Good morning, class, and welcome to our continuing lectures on sustainable energy technology. In the previous class, we started our discussion on energy storage, which is a critical component of the energy transition to renewable energy systems in order to solve some of the associated challenges like intermittency, variability, etc. So today, we will start our discussion on the various types of energy storage systems available, and we will we will discuss them one by one and look at their various advantages and disadvantages. The first class of energy storage systems is mechanical energy storage technologies. So these technologies utilize mechanical potential energy like gravitational potential energy, pressure, and inertial energy to store energy in the chosen medium. So, mechanical energy storage systems use physical means of energy storage like gravitational potential energy, energy associated with keeping something at high pressures, inertial energy, etc. to store energy in the medium of choice. Okay. So we will discuss three types of them one by one in the following lectures. The first is pumped hydro storage. Okay, we discussed a little bit of this during the hydel power plant discussions as well. We will go over it once more as it is a class and a very popular class of energy storage technology. The second type is compressed air storage. So these are storing compressed air and using it to generate energy in a way that we will discuss in a few, probably in this class only. Then comes flywheel based energy storage systems. So we will discuss what flywheel based energy storage systems is in the subsequent classes. So first let us look at pumped hydro storage systems. So what is pumped hydro storage? Basically it is using the gravitational potential energy of water as the storage medium. So what we are doing here is electrical energy is being transformed into gravitational potential energy of water, and then this gravitational potential energy is transformed back into kinetic energy of flowing water and this is transformed back into electrical energy. So as we have discussed before, electricity is used to run a pump which transforms the energy into then the pump is used to push water up into a high altitude reservoir. So the energy of electrical energy is converted into the gravitational potential energy of this water at high altitudes. Then when electricity demand is high, we are allowing this water to flow back through the system, and then the pump is acting as a turbine, and the flowing water that is coming down an incline is basically rotating the turbine and generating the electrical energy back. So electrical energy through a pump is converted into gravitational potential energy of water. This is converted back into kinetic energy of flowing water, and this is converted back into electrical energy. So this here is the pump, and this here is turbine. Okay. So if you look at the figure associated with this, how a schematic may look like, you will have something like this. This is your reservoir. And this reservoir is up in incline, and this is the pipe. This pipe is transferring water down from the hill, and this is your pump or generator based on how it is being used. And with this pump or generator is your electrical distribution. And here the pipe is flowing down into a lake or river. So basically then when you have excess electricity, that electricity is moving into the pump or generator from the electrical distribution grid, and this pump and generator is then pushing the water up the incline like this, and it is filling the reservoir. Okay, so the electrical energy is expended to push the water from the lake or the river into the reservoir. And when you have extra demand and lower production, then water is pushed back down using our turbine, and in this case electricity is being generated by the pump running in reverse. So we are getting back electricity, and this electricity is flowing back into the grid. So the basic operating principle in words is lifting water from a lower level to a higher level reservoir. Energy is charged. So if we use the language that is always common with energy storage systems, we are basically charging the energy storage system when we are putting water into the high level reservoir. So this is the high altitude reservoir. It is charged as water is used to fill up the high altitude reservoir. Okay. Then in times of high electricity demand, water is allowed to flow down and its kinetic energy is used to drive hydro turbines to generate electricity. Now here if we look at a typical case, so for example assume that density of water is 1000 kg per meter cube and we have a reservoir at height h equals to 400 meters. Okay. So energy stored by pumping 1 meter cube, which is 1000 liters of water, up to 400 meters, and assuming no losses, is E stored equal to rho W into the total volume of water into G into H equal to 1000 into 1 meter cube. So 1000 kg per meter cube and volume is 1 meter cube into 9.81 into 400 equals to 3.924 megajoules, or this is equals to 1.09 kilowatt hour. Okay. So this is the energy that if you store 1 meter cube of water at a height of 400 meters, then the energy that you are storing is around 3.925 megajoules or 1.09 kilowatt hour. Now usually a reservoir will be quite large. It may be thousands, tens and thousands of meter cube in its volumetric capacity. So you can see that a pumped hydro system can store multiple gigajoules of energy as and when required. So this gives some of the main advantages of pumped hydro storage. So firstly, water is abundant, inexpensive, and easily transportable in pipelines. So the main energy storage material is also one of the most easily available material in the world. It's water. It can be easily transported, easily stored, very inexpensive, and hence it is a very easy to use it as an energy storage medium. Water has high density compared to other fluids, and hence the amount, hence let's just rewrite this. Pumped hydro storage systems have very high volumetric energy storage density. So as we saw in the previous case, this 3.9 megajoules per meter cube of water is the energy density of the storage system, right? So it has a very high volumetric energy storage density. For just 400 meters of height, 1 meter cube of water will store around 4 megajoules of energy. It's one of the highest volumetric energy storage densities among the various energy storage systems. Hence, large capacity as large high altitude lakes and reservoirs can store millions of meter cube of water. Okay, so it has a very high capacity. A relatively large reservoir or a natural lake that is present in mountains will have water storage capacity millions of meter cubes. So you are getting energy storage capacities in terms of millions of gigajoules, even millions of kilojoules, millions of megajoules. Okay, so that makes it a very ideal for large capacity energy storage system. Finally, can store energy over very long periods of time, that is, has very high self-discharge times. Because once water is stored, and especially if your reservoir is reasonably covered up, there is very little water loss due to things like evaporation, etc. Okay, so you can store energy in a high altitude reservoir or lake for periods of multiple years. Okay, so it has very low, very large self-discharge time. You can store energy indefinitely without reducing the amount of energy that is being stored, and hence it is extremely good for long, large capacity storage systems. Okay. So, pumped further, the fifth advantage is it pairs well with local hydroelectric power systems and can also work with large solar and wind farms that are located in hilly regions and close to natural rivers or lakes. Okay. Now, as we discussed during the wind turbine systems, wind farms can be usually placed in high altitude hilly regions, and in hilly regions you will also find natural lakes and rivers. Okay, so it pairs relatively well with wind farms and even solar energy, where you have local hills, local changes in altitude, where you can create your artificial reservoir at a high altitude position. Okay, especially it works well with local hydroelectric power systems, because you already have the pump, the turbine, the dam infrastructure, and the rivers are usually in the, and these are also usually in high altitude areas. So in all of these cases, pumped hydro is a natural energy storage medium of choice. Okay. Pumped hydro. The last point is the pipes and pump turbine systems have very long lifespan before needing replacement. Hence, a pumped hydro station has very long storage lifetime. Okay. So clearly the pumps, the turbines, the pipe systems can last for very long, many decades and years. So the lifespan of a pumped hydro-based storage station is very, very long. Okay. So now we can look at some of the disadvantages as well. So first disadvantage is the total efficiency of such a system. So if eta P is the efficiency of the pump, which is usually of the order of 0.7, eta TR1 is the efficiency of flowing water up the reservoir through pipes. So this is of the order of 0.95. Then you have eta TR2, basically transmission 1, transmission 2, efficiency of flowing water down the reservoir through pipes, of the order of 0.92. So eta TR1 and eta TR2 are basically frictional and turbulence related losses in the flowing of the water up and down the piping system. Okay. Then you have eta T is the turbine efficiency. when the pump is being reversed and is working as a turbine, which is around 0.75. So the total efficiency is eta equals to eta P into eta TR1 into eta TR2 into eta T. The pump efficiency, electricity to pump. Turbine efficiency, efficiency of the energy from the kinetic energy of water that is being transmitted into electricity. Okay, so the generator and the motor efficiency are also included in the pump and the turbine efficiency. Okay, it's not just the efficiency of the pump blades or the turbine blades. The motor efficiency, converting the electrical to mechanical work, and the turbine generator efficiency, converting the rotation of the shaft to electrical work, is also being considered. So then this becomes of the order of 0.7 into 0.95 into 0.92 into 0.75. So this is of the order of 0.46. So typical round trip efficiency of a pumped hydro system is less than 50%. So 50% of the energy is being lost. Okay, so if you are if you initially input say 1 gigajoule of electrical energy into your pumped hydro, you will only get around 0.4 to 0.5 gigajoule of electrical energy back. The rest will be lost due to inefficiencies in the system. Okay. The other, so pumped hydro has relatively low round trip efficiency. Okay. The other issue is slow response time. So pumped hydro systems take time to start up, fill reservoir, and reverse to turbine mode. So it is a slow response energy storage system of the order of half a day, etc. Okay. So when your demand is high, you have to turn on the pump, push the water up into the reservoir, and then when the demand drops, you have to switch back the operation and put it back into the turbine mode and generate electricity. So that storage and reversal process, one cycle, can last several hours or half a day even. So it's a slow responding system. Okay. Fast changes in demand supply cannot be tackled by pumped hydro systems. Okay. So used for large grid scale energy storage that caters to predictable and slow shifts of large scale changes in demand and supply over periods of days, weeks, or even months. Okay, so it is possible. So for a hydroelectric system, you get a lot of energy that can be generated during the rainy season because of the high flow rates of water in the river. So there you can have an auxiliary pumped hydro system which stores a lot of that water up into a high altitude reservoir and hence stores that energy during the rainy season, and then releases that excess water during the winter and the summer times when the demand is high for electricity, but the river flow is too low to create sufficient electricity on its own. Okay. It can also cater to large scale weekday, weekend kind of changes in energy demand, and even diurnal changes like changes from the late evening to early morning, those kinds of changes. So those kinds of changes can be catered to, but fast response like on the scale of seconds, minutes, or 1 hour or less than 1 hour, those cannot be catered to by this pumped hydro storage system. Pumped hydro is the largest energy storage medium currently used in the world. So of the storage capacity that has been installed worldwide, pumped hydro is the leading one. Okay, and this is expected because this is one of the storage systems that is particularly suitable for large scale storage. So when you are designing it, you are designing it for hundreds of megajoules of energy storage system. So we will stop here today. In the next class, we will discuss compressed air energy storage system. Thank you for listening, and I will see you in the next class.